In the previous classes we have discussed about the micro operation, register transfer micro operation, inter register transfer, and in that case we discussed about bus transfer and memory transfer. Next we can discuss about arithmetic micro operations. The basic arithmetic micro operations are addition, subtraction, increment, decrement, complement and shift. Addition micro operation can be represented with the plus symbol. For example, R3 gives R1 plus R2. Subtraction micro operation can be represented by minus symbol like this, that is R3 gives R1 minus R2, or by a 2's complement addition, that is R3 gives R1 plus 2's complement of R2, that is the R2 bar plus 1, that will form the 2's complement of R2. Okay. Then 1's complement operation can be represented like this, R2 gives R2 bar. 2's complement will be like this, R2 gives R2 bar plus 1, we already discussed. Increment micro operation, R2 gives R2 plus 1. Decrement micro operation, R2 gives R2 minus 1. This increment and decrement micro operations can be implemented with a up counter and a down counter. We can consider two register transfer logic statements. T2 colon A gives A plus B, T5 colon A gives A plus 1. And this T2 and T5 are timing variables that is related with the clock signal. So this is actually a control function. All the variables or all the expression just before the colon forms our control function, and this will be our micro operation. Okay. So anyhow, T2 colon A gives A plus B and T5 colon A gives A plus 1. Then what will be the equivalent hardware implementation? We already discussed that corresponding to each statement, a register transfer logic statement, there will be an hardware implementation. So this is the hardware implementation corresponding to these two statements. We have register B, register A, and a parallel adder. Both the register B and register A are connected to the parallel adder. So this parallel adder will perform addition of A and B, and that sum will be always available through this bus. But this register A is controlled by a load input. So whenever this load will become 1, then only this input will be captured into the register A, and that load input is controlled by T2. Similarly, there is another input control line, increment. So whenever this increment line will become 1, the register A will act as a up counter and the value will be incremented. So this increment line is connected with the T5 timing variable. So whenever this T2 timing variable will become active, the sum will be captured into register A. Similarly, when T5 timing variable will become active, then at that time register A will be incremented by 1. That is the same operations. Next we can discuss about logic micro operations. Specify binary operations for a string of bits stored in registers. This actually specifies a bitwise operation. These operations consider each bit in the register separately and treat it as a binary variable. The different logic micro operations are OR micro operation, AND micro operation, complement micro operation, and XOR micro operation. These are the major or 4 logic micro operations, and we can derive other logic micro operations by using these 4 basic ones. And first we can consider the OR micro operation. This OR the symbolic designation is this one, OR symbol. R3 gives R1 or R2. This is the register transfer logic expression corresponding to OR micro operation. So if we can, for example, we have two data, this one and this one, these are the two register contents. Then if we perform OR, then a bitwise OR will be performed and we will get a result. the implementation can be done with the help of a OR gate, with the help of an OR gate. Okay, so here 0 0 0 1 1 1 1 1 1, then 0 0 0 0. Okay, this like that bitwise OR operation will be performed. AND microoperation, symbolic designation is, this is AND symbol. R3 gives R1 and R2. This is example. The bitwise AND will be performed, and hardware implementation can be done by AND gate. These gates are, I think you have already studied in switching theory and logic design subject. And complement operation or not microoperation. Symbolic designation is R1 gives R1 bar. Example, each bit will be complemented. 0 will become 1, 1 will become 0. Hardware implementation can be done by using an inverter gate or NOT gate. And another gate is, or another microoperation is XOR microoperation or exclusive OR microoperation. Symbolic designation is R3 gives R1 plus R2. Example, this one. In this case, if the two bits are same, then 0 will be output. If the two bits are different, then 1 will be output. Here 0 0 we will get a 0, 1 1 we will get a 0, 1 1 we will get a 0, then 0, next bit is 0 0 we will get 0, next is 1 0. Okay, next bit is, okay, based on the bits. If the bits are 0, both zeros, then we will get a 0. If the bits are both ones, then we will get a 0. If they are different, then we will get 1 here. Hardware implementation by using an XOR gate. And the hardware implementation of logic microoperations requires that logic gates be inserted for each bit or pair of bits in the registers to perform the required logic function. That is, for example, if we want to perform logic AND of two registers A and B, and they have 4 bits in each of the register, then for implementing this we need 4 AND gates for performing the logic OR of the two registers A and B. That is, corresponding to each bit pair we need 1 AND gate. Most computers use only 4 microoperation and or XOR and NOT, from which all others can be derived. Logic microoperation hardware implementation we are combined all of these gates into a single unit, that is with the help of a multiplexer. So XOR gate is connected to the 0 input of the mux, and AND gate is connected with the 1 input of the mux, OR gate with the 2 input, then NOT gate with the 3 input. This is our output. So based on the working of the mux is based on the select line, any one of the input lines will be available here. So the input to each of these gates are AI and BI. We assume that A is a register and B is another register. Assume that they are n-bit register. A is an n-bit register and B is another n-bit register. So if we want to perform any of the logic operation on these registers, we already said that we will perform a bitwise manner. So AI and BI indicates the ith bit of A register and B register. They are connected to the gates like this. So if we are giving a 0 0 here, the XOR of AI and BI will be available here, that is here. And if we are giving a 0 1, then AND of AI and BI will be available here. If we are giving a 1 0, then OR operation will be performed. If we are giving 1 1, complement operation will be performed. Here only A is connected in this case. This is for 1 bit, not for pair. So this is corresponding to 1 pair of bits. For performing the entire register, we need a number of copies of the same unit.